What if I told you that light doesn't actually travel? Pause for a second. Let that sink in. We all imagine light moving from one place to another, don't we? From the sun to earth, from a flashlight to the wall, from your phone screen to your eyes. But what if I told you that this common sense idea might be completely wrong? That the very thing you've taken for granted all your life behaves in a way you never imagined? And it's not just a weird thought experiment. It's a question that one of the greatest physicists of the 20th century, Richard Feynman, actually asked. Imagine looking at a beam of sunlight. You see it here. You see it there. You assume it traveled across the space in between. Right. That seems natural. Obvious. True. But here's the problem. No one has ever actually seen light moving. What we see is it appearing at a source, and then appearing somewhere else. The travel in between? That exists mostly in our imagination. This is why the idea is shocking. It feels like your brain is betraying you. Everything you thought you knew about light is suddenly questionable. Richard Feynman wasn't just a scientist. He was a curious observer of reality. He refused to accept things just because they were taught in textbooks. He hated memorized answers and complicated jargon. To him, if you really understand something, you should be able to explain it simply. And when it came to light, he asked the question that most people would never dare. How do we actually know that light travels? Think about it. You turn on a lamp in a dark room. The light appears instantly, almost magically. Where did it come from? How did it get there? Physics gives us formulas. Textbooks give us equations. But Feynman wanted to see the truth behind what we observe. He wanted to strip away assumptions. And what he found was a reality stranger than most people could imagine. So here's the challenge. Forget what you think you know about light. Forget the image of it traveling like a tiny bullet through space. In this video, we are going to explore Feynman's mind. We'll see how he looked at light not as a moving object, but as a series of events, emission and absorption, where movement is just something our brains fill in. By the end of this journey, your perception of reality, your understanding of time, space, and light itself may never be the same again. Before we dive deeper into Feynman's mind, let's take a step back. What do we think we know about light? From childhood, we've been taught that light travels straight, fast, from one place to another, from the sun to earth, from a flashlight to the wall, from your phone screen to your eyes. It seems obvious, true, and yet, this common understanding is exactly what Feynman questioned. Think about your everyday experiences. You switch on a lamp, and the room lights up. You see a star twinkling in the sky. You watch lightning during a storm. Every time, your brain automatically fills in the gap. The light traveled. It moves like an invisible arrow from point A to point B. This is what almost everyone assumes. It feels natural, obvious, true. But assumptions can be misleading from early school. We are taught the speed of light, 299,792 kilometers per second. We learn about rays, beams, reflection, and refraction. We memorize formulas about distance and time. All of it reinforces the same idea. Light moves like a tiny object traveling through space. But here's the subtle problem. Textbooks rarely ask the question Feynman asked. Do we really observe light moving? Every measurement we make is actually an observation of light being emitted or absorbed. The sun emits light. Our eyes absorb it. But the journey of light in between? We never directly observe it. It's a mental model, an interpretation, created by our brains to make sense of what we see. And because our brains are so good at filling gaps, we assume light is moving like a bullet. But assumptions are not reality. So, what does this tell us? The world we see is filtered through our minds. Our common sense about light is based on assumption, not direct observation. And that's exactly why Feynman's approach was revolutionary. He didn't just accept what everyone believed. He questioned it. He tested it. He observed it. In the next part, we'll step into Feynman's actual thinking and see how he used observation to challenge the very idea of light traveling. Now that we've seen how common belief shapes our understanding of light, let's step into the mind of Richard Feynman. Feynman didn't just question what everyone knew. He asked, how do we actually know it? To him, science was not about memorizing facts or repeating formulas. It was about observation, curiosity, and understanding. The universe as it really is. Feynman's thinking was simple yet profound. What do we actually observe? What do we imagine? When it comes to light, we observe emission and absorption. We see light appear at a source. We see it reach a detector or an object. But the movement in between? That is largely a mental construct. We assume light travels through space because our brains want continuity. But continuity is not the same as reality. Feynman explained that light behaves more like a series of events. A source emits a photon. The photon interacts with something else. It is absorbed. The actual path of the photon is not something we directly witness. In other words, light doesn't move the way we think it does. He called this the emit-absorb principle, and it completely challenges our intuition about motion. Feynman's thinking teaches us an important lesson. Don't trust assumptions. Don't be satisfied with what everyone else says. Look carefully at what is observed. When we do this, the world suddenly becomes stranger and more fascinating. In the next part, we'll dive even deeper into the physics, explaining why light doesn't travel the way we think, and what this means for reality itself. So far, we've explored common beliefs and Feynman's unique thinking. Now it's time to go deeper. To understand why light doesn't travel the way we imagine, we need to peek into the strange, fascinating world of quantum physics. But don't worry, we'll keep it simple. Because at the heart of Feynman's idea is something very simple. Reality doesn't always follow common sense. In classical physics, we think of light as a tiny particle moving through space, or as a wave traveling smoothly from one point to another. Quantum physics, however, tells a different story. Light is made of particles called photons. These photons don't follow a single path like a car on a road. Instead, they take every possible path at once, and we only see the result where the photon appears. Think of it like this. If you throw a ball, it follows one trajectory. But a photon, it explores all possible trajectories simultaneously, and the universe decides the outcome only when it's observed. This is why the idea of travel is misleading. We imagine a photon moving along a line. In reality, there is no single line. There are countless possibilities, all existing at once. The human brain, craving simplicity, fills in a straight path. It's not wrong to visualize it this way for learning purposes, but strictly speaking, it's an illusion. Feynman called this the sum over histories, a way of understanding all possible paths photons could take. Before the final event is observed, another shocking part. Time and distance don't work the way we imagine when it comes to light. A photon doesn't experience travel time like we do. From the photon's perspective, emission and absorption might as well be instantaneous. What we call speed of light is really a measurement of relationship between events, not a literal journey. This completely challenges our everyday ideas about motion and reality. Light doesn't travel like a ball or bullet. It exists as possibilities, only becoming real when observed. What we perceive as movement is our brain filling in the gaps. Feynman's deep explanation reminds us, reality is stranger than it seems, and observation matters more than imagination. In the next part, we'll look at real-life examples that make this abstract idea feel tangible, showing how photons behave in ways that defy common sense. So far, we've explored Feynman's thinking and the deep quantum explanation of light. But abstract ideas can feel abstract. Now, let's bring this down to earth. Let's see real-life examples where you can observe, or at least imagine, how light behaves in ways that defy our common sense. These examples will make Feynman's strange ideas feel tangible, even astonishing. Imagine you take a photo with a camera. The flash goes off, illuminating the scene. You see the light hit your subject instantly, or almost instantly. But here's the strange part. You never see the light traveling from the flash to the subject. All you observe is emission and absorption. Your eyes and the camera detect the photon where it appears. The journey in between? It's not observed. Your brain fills in the motion. It's the same principle Feynman emphasized. What you perceive as travel is largely imagination. Let's scale up. The sun emits light, 150 million kilometers away. We see daylight. We know it takes 8 minutes for sunlight to reach Earth. But remember, we don't see the photons traveling. We see the sun shining and then sunlight arriving. The journey of each photon is invisible. All the paths photons could take, countless. Yet our minds automatically picture a straight line from sun to Earth. Feynman would say, that straight line is a story your brain tells you, not reality itself. Now, think about ordinary moments. Lightning during a storm, turning on a light switch, watching a flashlight in a dark room. In each case, light appears at a source and then at a target. You never observe the intermediate path. You infer movement, because your brain is wired to connect dots. Even in everyday life, reality is stranger than it seems. So what do these examples teach us? Light doesn't move the way we imagine. Our brains create stories of motion. Observation, not imagination, is the key to understanding. Feynman's examples were often like this. Simple, relatable situations that reveal the deep, hidden truths of the universe. We've explored the mystery of light, common beliefs, Feynman's thinking, quantum explanations, and real-life examples. Now, it's time to step back and ask a bigger question. What does all of this mean for life, learning, and curiosity? Because Feynman's lessons are not just about photons and equations. They're about how we approach reality itself. Feynman constantly reminded us. Never accept something just because it's common sense or everyone believes it. Light doesn't travel like we imagine. Our brains fill in gaps. Observation is reality. Assumptions are not. In life, this applies everywhere. Don't blindly follow tradition. Don't accept half-truths. Look carefully, observe deeply, and think critically. Feynman loved asking why. Over and over. Why does light behave this way? Why do we think it moves like a bullet? Why do we assume what we cannot observe? Curiosity is not just about answers. It's about the journey, the act of questioning itself. And this curiosity makes life infinitely more fascinating. By studying light, Feynman discovered something profound. Reality often defies intuition. What seems obvious may be wrong. Observation is the key to truth. If you carry this lesson into everyday life, you'll notice hidden patterns. You'll question assumptions. You'll see beauty in the unexpected. So here's the final takeaway. The story of light teaches us to look carefully, think deeply, and never stop asking questions. Feynman's insights remind us that reality is not always what it seems. Sometimes, the journey of understanding is far more important than the answers themselves. So the next time you turn on a light, look at the sun, or see a flashlight in a dark room, pause and wonder, how do I really know what I see? What stories is my brain filling in? What mysteries am I taking for granted? Embrace curiosity, challenge assumptions, and never stop exploring. Because that is the true lesson of Richard Feynman and the mystery of light.